Thank you. It's great to be here in this fantastic workshop. So today I want to tell you about materials. It's a topic that we haven't heard too much in NeurIPS, but if you think about the challenges of the 21st century, and you think about, for example, water filtration or drug-resistant bacteria, or perhaps light harvesting or energy storage, there's going to be always a materials component. And with the emergence of tools like robotics and AI, you might wonder what would be the role of them in the discovery of such needed materials. So one of the possible motivations of doing AI for materials is basically altruistic, you want to save the world. And the other one is perhaps to make money. Barron's is an investors advising magazine that all these rich people actually read. And it says there are actually $3 trillion opportunities in the market for in the near future. One of them is CRISPR gene editing, one of the other ones is quantum computing, and the other one is AI for materials. So I was very happy when I saw this article because this article and also this article in MIT or about how AI is reinventing the way we invent point out that one thing is to do AI for like social apps and like all this stuff that is on the internet. The other one is using AI to transform our physical world. After all, we consume materials all the time. And arguably, the latter is actually a larger market. So this is a good opportunity for a lot of you young people thinking about where you can make an impact. So what are the challenges in the space of materials, roughly speaking? If you want to think about the set of all the possible molecules and materials that we can make, there's been many estimates, but let's use one of the numbers out there. It's about 10 to the 180 possible ones. It's in principle an infinite space, but practically we're bounded by the number of chemicals you can buy and the amount of time it takes to actually make the molecules. So we're bounded in terms of human testing of these materials, and the space is estimated to be 10 to the 180. Just to remind you that the number of atoms in the visible universe is 10 to the 80. So this is really telling you that this is an immense number. So in my research group and other research groups around the world, people can actually use machine learning on the order of millions of molecules routinely. Like if you want to do ML in a project, you can download a data set of 80 million molecules or 1 million molecules and so on, and you can actually do research on that type of data set. If you want to run quantum chemical calculations on them to actually generate new data or validate your models or look at new properties, roughly 100,000 molecules is what you can do in a reasonable amount of computer time. We have actually done experiments like we actually developed something we like to call molecular Tinder, like an app that humans are actually using to interact with molecules. And the same as in Tinder, about 1,000 swipes and you don't really care anymore about what's going on. So humans have an attention span, and therefore if you use humans to classify molecules, it's actually pretty hard. And even worse, actually making the molecule, testing the device is of the order of tens in most of my projects. So that basically means that we have this huge logarithmic funnel, right, of all the possible chemical space to the actual molecules that are tested in any materials science project. So my own personal interests have to do with optoelectronics, like organic displays and this type of things, but also in energy. So I'm going to show you an example in the space of batteries. Humans have not stored energy at the massive scale. And if we want to go to the clean energy transition, we're going to have these very large tanks full of material that actually stores energy at night and then releases the energy at the day, for example. Stores energy during the day and releases energy at night, for example, or at places of high load or low electricity load. And these things are called flow batteries. And the requirements for flow batteries are really stringent. They are different than the regular cell phone batteries in the sense that we really want to have a low cost per watt and per watt hour. And to do that, basically, we are basically limited to water-soluble materials. And about 5 years ago, we started publishing on the idea of using organic molecules as possible candidates for storing solar energy. So we started the field of organic flow batteries. Of course, in a collaboration with experimentalists and engineers, chemists, myself, which I'm more of a theoretical person, we developed this early flow battery at Harvard. And the reason I'm telling you that story is that it took us about 5 years, about 1 million molecules screened in the computer, about 140 molecules made and tested in devices, to actually come up with a molecule that actually, based on our initial papers, already satisfied all the requirements for one of the sides of the battery. That means that, we were very fast, but that really means that to do the other side of the battery, there's going to be another $5 million, another 5 years of work, a team of 20 chemists. And they argue we don't have time, right? We need to be faster. So this is where AI and robotics comes in. So we ran a huge workshop in Mexico City under the context of Mission Innovation, this global initiative under the Paris Agreement to try to curb climate change. And on that framework, we actually brought 50 scientists from around the world, and we actually wrote a report. We identified some of these barriers, right? I mean, if you want to make the molecule by a human, the problem is actually the human is intelligent, and therefore sometimes they change the molecule. They're slow, expensive. So we started thinking about these platforms, right? How can you actually reinvent molecular discovery from beginning to end, right? And of course, people in pharma have thought about it as well and in other contexts. But this is basically our goal. Our goal for the field, and there's many chemists and computer scientists more and more in this field, is to take the typical process of 10 years and hundreds of millions of dollars to get a material to market. And I usually use a couple examples from our own work. But obviously, there's work from many other people. For example, bringing a solar cell to market was about 25 years, okay? For example, from the discovery of the solar cell to the first solar cell built. For the discovery of the first gallium arsenide LED to where it came in the market is about also 25 years. So the materials that we're discovering today will be in the market when I am 70, I'm 43 right now. So it's pretty pathetic, right? So to accelerate that, then you actually want to think about the pipeline, and this is making the molecule, making devices with the molecule, testing them, scaling, and then manufacturing. So if we can get a factor of 10, and that's actually pretty simple factor, right? I mean, you just have to get a factor of 2 in each, or 3 in each one of these different layers. You could, in principle, change completely the way we discover materials, because now 1 year and $1 million is actually much more attractive to venture capital, and even 1 month and $100,000, which is another factor of 10, really unleashes the power of molecular discovery, right? And we will imagine having new plastics, new materials, new things all over the world. So that's kind of like the mission that we're all into. And therefore, in this paper with Benjamin Sanchez, which by the way is also from Mexico, my former grad student, he now works at Google, we wrote a perspective where we show you, I mean, this is an example of a flow battery that I just told you about. And this is an example of what I like to call a self-driving laboratory, right? So like the same thing as a self-driving car. It's a lab that is making decisions as soon as it gets data, right? And it's actually being intelligent about what's going to be the next thing it's going to be doing. This is different than what people did in the 90s and early 2000s called high-throughput screening in chemistry or in biology, where people just ran a lot of experiments and then did data science on them, right? That's really nice, but what we argue is that as you get the data, you can steer what experimentation is happening, and therefore you reduce the number of experiments and reduce the amount of materials and time that you use. Is this even possible? Well, the answer is actually yes. Another field, biology, has been able to do that. Just by using automation and data science, they have been able to lower the cost of sequencing the human genome from $100 million to perhaps $1 million over a time span of 15 years. This goes beyond Moore's law, and now you can sequence your entire genome for under $1,000, right? So that is fantastic. So if the biologists were able to do it, how come the material scientists and the chemists cannot, right? So this is kind of like a challenge to my field, and which we have to take it. And we have only about 12 years or even 11 years to actually avoid the irreversible problems of climate change. So arguably for all of you, this is kind of like a pep talk. This is another important use for your AI skills, right? Rather than tagging image of dogs and cats, right? Maybe you want to tag materials to save the planet. So in our workshop, we actually came up with a recommendation of actually coupling automation in characterization and synthesis with, of course, HPC and machine learning. And today, I'm not going to talk too much about it, but in my lab, we're developing a package called Chemos. You can think about it as a framework, like as a PyTorch or a TensorFlow for experimentation, right? So it's based on machine learning tools, but also has access to databases, access to HPC resources, controls robots, and it's kind of the operating system for chemistry, right? So it's kind of like a lightweight tool that actually allows you to actually plug into experimental laboratories and actually do experiment. In pharma, if anybody comes from that field, and by the way, they're hiring AI people like crazy, so you guys, next time for the next year, you should have pharma sponsors, you know. Actually, that would be a good idea. So they have this make, test, design, analyze cycle, right? Design, make, test, analyze. So pharma itself, to take a drug to market is about $2 billion. So they are also trying to cut their costs, and they're trying to do as much as possible of the drug development process in parallel by using AI. So this is a big transformation for a big industry. So I told you about the materials and chemical industries, but also the pharma industry is undergoing this AI transformation. And of course, they need a lot of people. So in Mexico City, we wrote this report that you can download. You can see there, take a selfie of a photo of this thing. These were some of the recommendations, and today I decided to focus on the so-called inverse design problem in chemistry. And we had a talk about the inverse problem here, but it's a slightly different way of talking about what is inverse. Okay, but it's the same idea. Okay, I'll tell you about it. The most important thing first is we had a talk actually earlier today about molecular representation. A molecule is a complicated object. It's a flexible three-dimensional object that has many poses or many conformations, many low-energy ways of exposing itself to the world, and it's actually moving all the time. Actually, you probably don't know that, but the reason the eggplant is purple is because it's oscillating between two different shapes that absorb energy at different colors. So there's no single shape of eggplant that is actually purple. It's the average of its motion that makes eggplant purple, which is kind of hilarious, right? But that's what happens. So how do you represent the molecule? I mean, it's many conformations. Can you represent it as a bag of bonds? We heard in the previous talk a bag of words. So there's a concept of a bag of bonds. You can represent it as a three-dimensional geometry. You can actually take its quantum mechanical density. You can use graphs, and we had many talks in this symposium about graphs. Or you can use text, smiles. And we start with text, and we go to graphs, and we'll end back with text. A lot of this talk will involve different molecular representations. So one of the biggest things first is representations, right? Then you're going to move on into models and so on, right? So very early on, with my colleague David Duvenot, when he was a postdoc at Harvard, and then Ryan Adams, when he was there, he's now at Princeton, they taught us machine learning to my lab. Actually, I was a very lowly chemist, only doing quantum computing, but these guys are the ones that taught me how to do machine learning. And we wrote this paper, I mean, based on the ideas of David, of looking at what the chemists used to call a Morgan singular fingerprint, which was this recursive fingerprint I'll show you graphically in the next slides, and make it differentiable and vector-like, like instead of having discrete numbers, it was now a continuous vector that is using softmax and things like that. So modernizing the way to actually represent molecules. But I like to point out that the chemists already had the baseline of the idea, and basically this is kind of like, in some sense, this model reduces to this model, as you can see in this paper. Okay, so that's the beginning of it all. And my student Benjamin now works at Google with Alex Wilczko and Jennifer Wei and others. And he made this beautiful kind of GIF that you can see there in the Google AI blog of actually a molecule, for example, vanillin, and actually all the features that actually are put in one of the nodes of the graph that then are actually collated into further nodes of the graph by this learnable representation that is differentiable, right? What is different between the chemical models and the new modern graph convolutional neural network models is that obviously for the task at hand, you're going to train these layers, okay? So the chemists didn't used to do that. They used to have like kind of like the equivalent of a random layer, right? And then of course all of these are going at different length scales. First the atom, then the next nearest neighbor, then the next nearest neighbor, and so on. And they're all collected into a vector, and then you use for prediction. And in the case of this paper by Benjamin, I'm also a co-author, but it's mainly the work of Google, is basically predicting, for example, features of smell. Is this molecule chocolatey, or it smells like tequila, or something like that? How do these graphs have evolved? So it's very interesting because since 2005, obviously, there's a lot of people that are using them for machine learning in molecules. And I really like this paper by Rishi Kondor, where he actually takes some of the invariants of the graph convolutional networks and then builds a tensor model that is qualitatively better than most of the different models based on our neural graph fingerprint, which is the one that we introduced and I told you before, and get you better mean absolute error and RMSE on the so-called Harvard Clean Energy Project, a data set that we developed a long time ago. This is one of the early data sets of molecule to performance that we released a long time ago. This is a paper that was in the archive since 2016 and has created a lot of attention. A lot of people are working on it. It's the idea of actually using autoencoders or generative models to actually look at chemical space. You can take a molecule, which is a very interesting graph object. In this case, I'm going to use its sequence representation, and you're going to compress it into a roughly 200-dimensional latent space, and then, of course, decompress it. So as chemists, I love this because it goes from discrete to continuous to discrete. And therefore, I can use this type of model in the same way that, of course, people have developed text autoencoders. But now, in this particular case, instead of text autoencoders that, for example, You can interpolate in the text autoencoder the meaning between two sentences by moving in the latent space. We want to do the same thing for chemicals, right? Can we use latent spaces for chemicals for using molecular design? And for that reason, we're using molecules as text. So this is a representation called SMILES, introduced in the 80s, and we'll come back to it at the end of this talk. But SMILES is kind of like a shorthand way of actually converting the graph into a sequence. And therefore, you can use sequence models to represent, for example, this molecule, which is called, for example, sugar here. Okay? So what we did in this paper was actually to latch another model, could be a Gaussian process or a neural network or whatever favorite model you have here, to the latent space, and then to use this model to actually optimize a property, right? So in this particular case, therefore, what you can use the autoencoder for is to actually move to the maximum of that particular property and then project back into the latent space and decode what is the optimal molecule for that particular property, right? So that takes you to kind of like stages of my research group, but also I think the field of going from this high throughput screening stage when you're actually sending a lot of points and trying to get 1 point for the inverse design, and inverse design for us means from property to structure, right? To the computer-guided Bayesian optimization and autoencoder-based type of idea of trying to minimize the number of experiments and get to the highest property as soon as possible. So you can, for example, just use a VAE and sample. So in this case, if I sit on this molecule, which is ibuprofen, a very important molecule after you drink a lot of tequila, right? So you actually sit in a point and then start sampling. You will actually get, because of a variation nature of this autoencoder, you're going to be getting stochastically molecules that are close to that particular encoded space. And actually, you can actually look at the typical molecular distance. This is a Tanimoto distance. And what you get is kind of like a 200-dimensional Saturn ring of data. So the typical molecules are about Tanimoto distance of about 17 or so. From all the other molecules, you can see here a few molecules in the tails of this distribution that are very close to ibuprofen, and you can just move on to the maximum. So if you want to interpolate between molecules, you kind of want to move in this kind of cloud of data points, and Benjamin did beautiful work on that. But also you can actually hear, for example, a two-dimensional projection of the latent space, trained to make synthesizable and drug-like molecules, coupled to a Gaussian process, was the best model that we used, sampled from 2,000 points of the latent space, allowed us to very quickly optimize in the latent space virtually. And I'm happy to report many groups now use this as their QED minus SAS became kind of like the blind, I am a machine learning person, I don't know any chemistry, I want to use this. So they are using these features from my early kit. But I am a chemist, so I want to use this to actually make materials, make molecules, make drugs, actually test it in real lab. So this is where a collaboration with Silico AI came along, and Silico AI is one of these top AI startups in pharma. There's, of course, Benevolent AI and Atomwise and Silico. There's a few of them that are trying to do more or less the same thing, right? Which is basically take a target, for example, in this case, a DDR1 inhibitor, and actually use AI to quickly go from ideation of the molecular space to all the way down to experimentation. So in about 40 days or so, we actually went from using this adversarial autoencoder, is basically a variant of the model I just showed you, all the way to testing in cells and organoids and then rats, and actually finding 3 lead candidates for DDR1 kinase. So this is really cool because it shows you that at least one of the stages of drug discovery can be accelerated with AI, right? And this just came out in Nature Biotechnology. Now, this is just a lead identification. It actually takes a lot of more work to actually take a drug to market. This is just a candidate. Many of these candidates will not work. You need to actually work in parallel, and of course, this paper has generated a lot of noise in Twitter and the internet. GSK now has actually another study, apparently it's going to come out with more molecules. So this is kind of like a rat race, so just to keep using the rat model to actually move into this space of drug design. We also actually introduced the first, or one of the first, solid state representation. Okay, so I just told you about molecules, but you also want to think about solid state materials, oxides, for example, periodic systems. So for that, we actually use a double autoencoder, one that represents a Gaussian image that represents where exactly the unit cell is formed, and another one where you actually represent where the atoms are in the unit cell. And we are not the first ones to use representations such as this one. For example, Isaac Tamblyn from Ottawa in Canada here has a similar representation for solids and other groups. But what we did is build the first kind of autoencoder for this, So again, it's a double autoencoder because we need to actually take the latent space of one to fit it into the second one and so on. And we classified here stable and unstable phases of material called vanadium oxide, which can come in different forms, right? They are called polymorphs, or they are called different phases of vanadium oxide, different proportions of vanadium monoxide. And what we found here is these are the most stable materials that are known. It's called the Convex Hole, the space of the most energetically favorable materials. But these are materials that were dreamed by the generative model. They were generated by this autoencoder, sampled. And I'm only showing you the ones that have these particular proportions of vanadium monoxide. And here are feasible 80 milli-electron volts per atom materials that could actually exist potentially that nobody has known about, right? So this is quite interesting because now you have another place where you can actually use these type of models to actually make predictions in the material space. Just advertising, Benjamin is going to present this on Saturday in the MLPS workshop. But basically what the Google team did, and again, I'm just very light collaborator, but takes one of these graph convolutional networks, and then in this particular prediction layer, you actually can look at the embedding space. So this is not an autoencoder per se, but it's actually just looking at the embedding space of one of these GCNs. And actually, if you look at the principal components of that, which is the way we like to actually plot chemical space, you can actually find the molecules that smell like cabbage or musk or lily or grape. Or actually, in this particular case, these are very, very sparse tags, so you can actually see how these tags are separated, using the kernel densities of this model. Or these more generic inclusive tags, of course, overlap. There's molecules that smell like two things at once, right? For different people, they will smell differently. But it gives you an idea, actually, that you can in principle use this for other design. And stay tuned because the Google team is actually actively working on that. Okay, and two former students of mine are there, so I'm very proud about that. Ben and Jennifer are actually working there. So obviously, this is not the only set of generative models that are out there. So Benjamin and I in this paper give you a bunch of models that you can imagine. I mean, very famous paper in Nature with Monte Carlo tree search was used to simulate retrosynthesis of molecules. That was a very important paper by Marwin Segler. And there's a bunch of people that are doing different things. I just want to tell you that, of course, you can use GANs, and this is our Mexican version of GAN. So the Latinx, I had to show you this. Mexican rover trying to fake money with a Mexican policeman, and of course, use access to reference data. These things happen. And basically what we did is actually very early on in 2007, right? We actually, based on this paper, we actually started that in reinforcement to actually make these drug-like molecules, for example, more soluble in this particular case. So here we started with original distribution, and here is when you make the molecules very, very soluble, right? So that gives you an idea of the kinds of things that you can do with one of these models, right? So now in the last few minutes of this talk, okay, so I'm not going to get into the robots, but I want to tell you a development that we'll talk more about in the MLPS workshop. And this was done by my postdoc Mario Kren that is here also, so you might also want to talk to Mario. You can find him in the WOVA app. But the idea here is that you have this SMILES representation that actually has a lot of different invalid strings. If I actually change this from a double bond to a single bond, or I remove a parenthesis, I'm going to have a typo. So what Mario was thinking is, can we have robust string representations of molecules? Because that will really change the way we want to think about molecular representations. And I'm proud to announce that, yes, we are presenting a workshop paper here, in what is called Selfies. Obviously, from SMILES, you have to go to Selfies, self-referencing embedding strings. We're very proud of the name, by the way. A speaker earlier on said he didn't like the name of his model. I really like the name of my model. So what the Selfies do is actually go from a Chomsky type 1 grammar to a Chomsky 2 type grammar. Okay? So this is a grammar that contains basically more context in the grammar. So the way you want to think about it is a subway map where you enter in a particular atom and then you're exposed to all the possible options that atom can bond to. Single bond, double bond, or all the types of atoms. So really, Selfies is a very simple rule vector that actually results, and this is the exciting part about Selfies. First of all, you can write the entire rules for Selfies in a piece of paper. And the second thing that is exciting about the Selfies is that they are 100% representable. Any random string is a molecule. So this has big applications for other types of graph networks. So if you're working in graphs, you should actually look at Selfies. Because in the paper, we not only look at molecules, we also look at quantum optics experiments and also other types of graphs. So you guys, if the graph is structured, then the only thing you need to do is to write these rule vectors and then use our code, which, by the way, you can use pip install and just work on it, and actually then transverse this graph and then build your molecular system, right? So basically, this molecule, you can tell Mario is a physicist because this is a very on-chemical molecule, but, you know. So it turns out, you know, this is a paper that is on the archive. We had some errors, some things that we needed to fix. So now the reconstruction of random strings in Selfies is 100%. Let me try to show you some examples here. Yeah, this is one that matters because I'm running out of time. This is one that matters. If you actually look at how many molecules, there's a way of estimating how many molecules are inside of the latent space, right? You move in the latent space volume and you try to integrate how many distinct molecules you can decode from an autoencoder. So this is going to tell you an idea of the power of your autoencoder, right? So it turns out if you actually use Selfies, you have actually, look, this is a logarithmic scale. You have, you know, several orders of magnitude, right? 3 or 4 orders of magnitude more molecular density, right? Which basically means you have a much more creative generative model, right? In other words, you are not wasting your neural network to actually try to learn the grammar of smiles or use complicated models like grammar VAE and other very complicated models that people have developed. But you actually use a very simple representation, right? So I argue in this talk and in general in my life that representation is key, right? For molecules, if you come up with a new representation, you're going to do very well. The models are secondary, right? If you use a GAN, for example, same thing, right? So again, the model is secondary, but this is a molecular GAN. And you can see how, you know, we reproduce much more valid molecules with the GAN, and you can optimize the GAN better using Selfies. And again, now the new Selfies version 2 is 100% valid. This is what's on the archive. And you can actually then just download it, install it. We're going to have a workshop in Toronto sometime in the spring. We're going to call anybody that wants to help us build the Selfies. We're trying to make them hyper-balanced. We're trying to make them represent, you know, standardized so that we can actually put it in all the chemistry packages. For example, we decided we're going to use Unicode to represent the molecule. So we're going to be able to use all sorts of symbols from any language and, you know, emoticons, whatever, all sorts of little pictures of cars or whatever to represent the molecule. So I believe it's going to be much more beautiful than the smiles representation in terms of visual representation. So if anybody wants to come and actually work with us in Selfies, please come to that workshop. And how much time do I have? Like 0? Yeah. So maybe in the last minute I'll tell you is like we also have, of course, oh, what's happening here? We also have a new work in the archive using evolutionary strategies. Because Selfies are 100% valid, then you can actually move to very simple things like evolutionary strategies and then modify the Selfie, right? And then we generate molecules and we have a fitness function that actually tries to kill molecules that have been around for a long time. Maybe what the planet is trying to do to humans now, right? Try to kill the humans that have been around for a long time. So we do the same thing for the molecules, so the genetic model is actually not happy with a particular fitness, right? So we have this discriminator to avoid stagnation. That's what I was trying to say. And then with that, because I ran out of time, I can just show you that our model, which is a genetic algorithm with this discriminator, kicks the butt of all the other models, including our own convolutional autoencoder, for actually generating unique molecules that are solvable in this case. Okay? So I recommend you to use at Selfies and generative Selfies and genetic algorithms. I think that's a very promising, very simple algorithm that you can employ. And with that, I'm gonna end showing you a picture of my research group. And thank you for your attention.